Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about friction stir welding. So let's dive deep into it. Now, first we have to understand what exactly is the problem that we are trying to solve via friction stir welding. Well, normal welding, that whatever you can think about, TIG, MIG, stick, laser, they are very hot and chaotic. And this is their nature. Like you cannot just like, oh, this I will work around this. No, this is by nature. So that creates an issue. Primary issue is high localized heating, meaning you are literally have a solid metal and liquid metal both existing at the same time with a boundary. That is not very comfortable for grain boundaries, microstructures. They do not like it. And again, thermal distortion is well known because again, ask anyone who actually welds something is like, oh, it's 90 degree. You weld it, it's like, becomes a potato chip. So that's a very serious thing. And many times you have to add filler material, sometimes you do not have to add it, but most of the time you do have to add filler material, basically a third party element. Basically you are joining two things and you are adding third material. That may not be desirable because again, quality control and alloy matching is not that easy. And gas and molten metals do not remain inert. A metal could be like, I do not react to oxygen. Here's it, put it to 700 degrees Celsius or 900 degrees Celsius or 1000 degrees Celsius, basically liquid metal, yeah, it will react with oxygen. So, and you're like, okay, what if I have flux gas like that stick? That stick is literally that flux provider, and TIG and MIG also have their own shielding gas. They are still gas, they are still reacting, meaning they could create trapped bubbles, porosity, those sort of things become a serious issue where you have to deal with this. This is by nature. So that's a big issue. And microstructures flat out do not like this, where it's like, oh, solid and liquid. Yeah, microstructures do not like it. You want all of it to be liquid and then slowly solidify, or like, that's the best way to get it. But if you are going solid, liquid, it's good. We have worked around it, but it's not desirable or optimal. So friction stir welding is basically, what if you create heat, but instead of using electricity or laser, you utilize friction. You basically go like this, friction. Now, here's the different part. If you are heating it up, what's the difference? Well, it's a contact welding, so you are only going to 70 to 90% of melting temperature. For example, let's just say you have an alloy. That alloy can easily handle, let's just say 1000 degrees Celsius. You're gonna only go to 900 degrees Celsius. You're not gonna touch basically full melting temperature. You will not. You will just behind it. Now, what happens to all metals when they reach this sort of temperature? They become what we call plastic deformation. Basically, they become plastic. You can just go, you can mix it like a dough. So that's plastic deformation thing, meaning metal generally become far weaker before they melt. So in that zone, you can do whatever you want to do. So you are doing stirring and diffusion. You're basically mixing two sides of the material completely with each other, right? Like just going like how we do with sourdough. So that gives you that original bonding. You're almost stitching it. So aluminum and dissimilar metals. Aluminums love this sort of process, and in some scenarios where you need basically, let's say, aluminum bus bar and then you need copper connector points, this is like, I got you, fam. And again, it works so well that it is on a different level. Like compared to normal welding, this is on a different level simply because of the grain boundaries. So if you are dealing with aerospace grade parts and you need very tight quality control, meaning I say this puppy will last, meaning this puppy has to last. Yeah, those sort of field love this. And you do not have any third party contamination. There is no filler rod, there is no fusion material. You are not adding anything extra. Basically, if you started with 100 gram, you will leave with 100 gram. You're not adding to it. And not to mention, there is no gas, so there is no porosity. And because the grain structures are not going from solid to liquid and then recrystallizing, the crystal structures is, of course, it does change. You are like plasticizing it and you are still talking to 70 to 80% of its melting temperature. It does change, but does not change in a way where it becomes too, you can tell where welding happened, like from a microstructure point of view. And some designs can actually make this into a reinforcement structure, meaning if, let's just say you have a sheet, you can run this basically stirring welding scenario and it will act like a ribs. It will like add extra strength. So fundamentally, like this is fundamentally different. And not melting it, basically not going from solid to liquid, that has a big deal. So how do we implement this? Well, one primary thing you must understand, this demands clamping. Meaning if you think, oh, we need clamps and no, this demands all the clamps. everything, meaning it should not even allow you to move millimeter by millimeter. Like in some demand, it may look like more harsh requirement than CNC. So it is brutal with clamps, like all the clamps. And machine has to be rigid, and basically so does the workpiece. Not only the machine should be able to physically, it's a contact, it's like so machine has to be strong enough to apply that force, so does your object. That's why it requires so much clamping. And RPM is not that high. You're not expected to go YOLO or like, you know, thousands and tens of thousands of RPM. You are only expected to like 800 to 1000 RPM. Again, some can go higher, but generally we do not go bonkers high. Although there is a lot of torque. We are talking some serious torque into this puppy. And the tool head, the basically thing that is making this marriage, that has to be the tool head. It's generally made out of material that is abrasion resistance, because again, you are talking about metal grains. It will sand away any material. So it has to be abrasion resistance and temperature resistant. So generally for aluminum, hardened tool steels are good choice. And if you have to deal with steel and all that, carbide could be utilized, or certain types of ceramics. It does require certain level of physical oomph, like you are physically brute forcing it. So you better be strong to do this. But it's not a complete process. Like laser welding is like you have the material, laser weld, throw it away, the end, done, process done. This is not like that. Generally, you're gonna leave a burr. A lot of people are trying in such a way that burr production is almost negligible. But just as a cautionary tale, you have to run a deburring process to it, so to say. Again, not a serious load or something heavy, but you do need to have it. So finishing process is a requirement, so to say. And temperature monitoring is critical, because you are talking about plasticizing and you are pushing it to that much. On energy level, you can go overboard and melt it. So that would be a big no-no. So you do require temperature monitoring. Nowadays, it's kind of easy. You can have a certain wavelength of thermal camera and just like look at it. Normal wavelength will not work because aluminum is reflective, but certain wavelengths allows you to see it, observe it. Or you could even have just like old school probes and all that. So it does require certain level of keeping eye on the thing, so you do not overboard it. Now, are there utilization of this? Yes, it's an ancient and abandoned technology, simply because the patent is ancient. The Soviet Union had the patent on Kimco from 1967. This is like old. This is like Apollo era kind of old. However, most people did not use it. Like ironically, electron beam welding had more use than this, so which is weird. And the Welding Institute in UK almost modernized it. That's what is credited to in 1991. And I'm hearing that more and more industry started to jump into it in 1990s. So in grand scheme of welding, every other type of welding is ancient. This is surprisingly recent. This is like it grew up yesterday. That's how recent it is. So in a, you know, there are not that many people who are expert with this, because this is so new. And no consumable, that's a very big deal for industry. That's like, hey, you're telling me that I do not have to deal with argon, nitrogen, or this or that. Shut up, take money. And tool, what about the tool? That also lasts a very long time. Of course not, because it's not gonna last as long as laser, because the laser is non-contact, but it does last long enough, meaning they say you can go up to 1 kilometer of weld before you have to do anything to it. So that's decent. That's like, we good. And absence of toxic fumes, spatter, molten metal, that allows, like, if you do this wherever laser is there, they will fire your ass. OSHA will fire missiles at you. But in stir welding, you can do that. Like, you can be just close. You can have children there, because be mindful, while you think argon is not a toxic gas, all gases are hazardous because they can displace oxygen. Meaning, let's just say you are in a welding shop and somebody or like the pressure regulator broke, or it slowly started to leak argon. Argon over time will displace every gas in the room over time, and you only have very small amount of oxygen in the room. Displacement will cause asphyxiation hazard and kaput. So trust me, people have passed away with that. That's how we know. So not having any gas, great. Not having any laser scatter risk, ultra great. Not having any fumes, GG. So this does help, like, meaning if you are dealing in a scenario where it's like everything is precise, everything is clean, this will not mess it up. So fundamentally, it's a very, what you call, worker friendly system. Although you do need clamps, as you can see, clamp, and more clamps. Like, you spend more time in clamping than the actual machine. Machine is like, done. Clamping is like, okay, we're gonna spend $1 million on clamping. Not even joking. and it is gravity independent. For example, let's say you are welding a pipe. Generally, people have to rotate the pipe. Why? Well, so weld spatter, the weld pool that is creating is held by gravity. If you go on the bottom side, yeah, it's difficult. It can be done, but it's difficult, and quality control goes down drastically. It's not impossible, but just try to avoid it if you can. This does not care. Like you are welding a rocket dome, you can weld it any shape, way or form. It does not care. So that is there. Anything basically that has aerospace or very strict requirement, this is your guy. This is the guy who's like, I got this. This is the only thing that can say, oh, you have like super duper hyper precise grade of lithium aluminum alloy and you want to mix it and you do not want to create a weak weld that has porosity issue or any sort of third party contamination. I got you, fam. You want to make sure that all your employees that are hyper expensive, they are safe, sound. I got you, fam. So Jeff Bezos is standing next to it. That's how safe this is. So that is the utilization part of it. So what can we expect in the future? Well, it is catching up to industrial giant. It's almost like industry has reached a point where laser is boring to them and laser is coming down to civilian use. And this is going to the industry as like, oh, this is the new thing, the new hip thing. And demand for better manufacturing is absolute. It will always rise. Again, working with the engine, it's painful. Let me tell you, it's painful. I want a system that just like put it there. It will do the welding without messing it up. That's the dream. So demand is always there. Even a little bit better, people are like, sure, to take money. So demand is always there. And advancement in automation. Like this is not ancient technology. So all the development that we had in last 30 years allows your CNC to work far more effectively, your cameras to monitor it effectively. Sensors are cheaper now. So quality control is not as unknown, as undifficult as it used to be. Heck, nowadays modern CNC can actually figure out how much torque they're applying. So that allows you to have, oh, am I actually mixing in the optimum zone or not? So that's a really good thing. Aerospace, every Tom, Dick and Harry is opening their rocket company, so that's going YOLO. Heck, even Honda is making it. And EV sector, they love this. While EV has issue with the battery being so heavy that they have to simplify the weight of everything else. So most cheap cars generally use steel, they have to use aluminum. So aluminum reduces the weight, battery adds the weight, you end up with the same thing. Actually, you end up with heavier vehicle because battery is so heavy, but you get the point. So aluminum, how do you weld it without any mess up or any issue and still have absolute top A grade quality? Friction stir welding. And power electronics, they love this. Because again, if you want to run basically a lot of coolant, you need to have pressure in some scenarios. Again, depending on the pump requirement, depends on cycling requirement, you may require it. At that point in time, you'll be like, okay, what the hell? If you have normal laser welding, it very likely to break apart and all that. In those sort of scenario, making heats, basically having a extruded aluminum as your main structure or die injection as your main structure, but you need to seal it up. Friction stir welding is like, I got you. Surprisingly large amount of electric vehicle inverters have this. I was thinking like, okay, aerospace, I saw this. I was like, no, electric vehicle, they're loving it. Oh, and not to mention, if you are dealing with oil, you could use stainless steel fittings. People like stainless steel fittings. They are far more robust. Thread on stainless steel fittings will last much longer than aluminum. Or even if you want to like, brace jointer or something like that. So wherever you have interface, you may want to have something that is more robust. So this does make sense for that. It can be done in household, but messy. It's not tuned enough. Again, nothing in the science is hard. Actually, it's easy. It's just that it's not tuned enough. Where it's like, okay, I'm going to buy this CNC programmer, this application, and this is the tuning. It's not sorted. Basically, it's the early years of 3D printing. It can be done, it's just not sorted. So, and industry, they are going all in, especially EV industry. So, if you want to jump into this world of manufacturing, this is the next hip thing. So this was my presentation on basically friction stir welding. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.